So, organic chemistry, the portion of crude oil. Let's quickly revise what we did yesterday, and afterwards we can start from wherever we left off. So, first things first, what is crude oil? When it comes to its origin, we do understand that millions of years ago, the plants and elements, the animals that living in the sea died, and with all the pressure and heat from the earth, they were converted into crude oil. This is a finite, non-renewable resource. If we're going to exhaust all of it, we cannot replace it easily since it takes millions of years to form the same huge amounts of this resource again. Now, what does crude oil contain? Crude oil contains hydrocarbons, which means the compounds that are made up of carbon and hydrogen only. And they actually have a lot of different types of hydrocarbons, varying in terms of size and masses and their types. When I say the types, I'm talking about saturated or unsaturated, means singly bonded, doubly bonded, triply bonded. All right. So they can range from any molecules, the molecules that have a few carbon atoms, all the way to molecules that have more than hundreds of carbon atoms in one place or in one molecule. So that's really a big, huge picture. When it comes to the physical properties, now number of carbon atoms per molecule is something that we emphasize upon because that's the way we categorize our compounds, and that's the way how physical properties of the compounds change. Now, remember that bigger is going to be the compound. By that I mean more the number of carbon atoms in a molecule, higher would be the number of attractions. If a carbon atom based molecule attracts with another molecule, that's as simple as it is. But if a big chain is attracting another chain, there would be a lot of attractive forces in between those chains. Bigger the chains, bigger will be the attractive forces into different points. We simply, for the sake of understanding of students, divide them into points that these are the attractive points that a chain has with another chain. So if there are four carbon atoms, four attraction points, one carbon atom, one attraction point, 100 carbon atoms, 100 attraction points, intermolecular forces of attraction become stronger and stronger, and it's actually difficult to pull one molecule away from its neighbors, which means they like to stick to one another since they are getting attracted by one another. So when the molecules become bigger, what kind of physical changes happen? We're going to go through that in this portion. First thing, boiling point increases. Since molecules like to stick closer to one another, and the larger are the molecules, the higher is going to be the boiling point. Why? Because there would be very strong attractive forces among them, and more energy would be needed to break those intermolecular forces of attraction and to produce something that is widely separated molecules in the gas, right? So if something is solid, just because the particles like to stick together close to one another, energy would be required to take the particles a little away in case of conversion of solid from liquid, and a huge amount of energy again would be required to actually take them far apart from one another, which is the conversion from liquid to gas. So basically, you're spending more and more energy to make sure that you can get that substance to boiling point. Hence, the boiling point increases. Now, in case of liquid, they become less volatile. Bigger the hydrocarbon, higher is the boiling point. This relates to the volatility. So slowly it is going to evaporate at the room temperature, which means less volatile. Again, this is because of the strong attractions between the molecules of that specific liquid. Another thing which is affected by being closer together, or we can say because of boiling point, is viscosity. Now, viscosity is actually the resistance to its own flow. We can't directly relate it to boiling point though, but we can directly, definitely relate it to the attractive forces between them. So they flow less easily, hence the word viscous. Liquid hydrocarbons with small molecules actually are very runny. Less number of attractive forces, of course, understandable, but the ones that have large molecules flow less easily because they have strong forces of attraction between them. Those forces actually play a role in posing resistance to its own flow, hence more viscous. The liquids become darker in color, of course, and bigger hydrocarbons do not burn so easily as the smaller ones. So this actually limits the use of bigger hydrocarbons as fuel, because we prefer them as fuels if we can burn them easily, and we do not prefer them as fuels if we're going to have a hard time starting them to burn, right? So we count a substance as being volatile if it turns to vapor easily at room temperature. This means it would evaporate quickly at room temperature. That's what volatility is all about. Moving on, separating crude oil. The crude oil itself has no uses. We can separate it into different parts. We call those parts fractions because the process that we use for separation is fractional distillation. Now, as soon as you hear the word fractional distillation, something must come in your mind, and that is to separate them on the basis of their boiling point. And right, that is correct. We're going to separate them on the basis of their boiling points, and every fraction or every part is going to consist of a mixture of hydrocarbons with similar boiling points. This whole process is carried out in an oil refinery. Our oil refinery has a big fractional distillation system that works its way with all of this, separating the crude oil into different parts. Now I'm going to read through the lines as well as through the diagram. The crude oil is first of all passed through a heater, as you can see at the bottom of it. Before we can send it to the fractionating column, we heat it up. And as you can see, the heating temperature gets to around 350 to 400 degrees centigrade. Now, which makes most of the hydrocarbons boil at that temperature. Now, what we do is that we start condensing them, and since they condense at different points, we let them pass through the fractionating column. They're going to rise as high up as their boiling point is lower. And they're going to stay over there if the boiling point is too high. For example, nothing happens to bitumen even at 400 degrees centigrade, so this falls like residue to the bottom of it. This is the residue since 400 degrees centigrade is not even the enough temperature to boil it. Then we have fuel oil, whose boiling point is closer to 400, diesel, which is far less than 400, then kerosene, even lesser, gasoline, even lesser, and finally refinery gases, which have the boiling points around 40 degrees centigrade or less. So they are actually trying to give you an idea how the particular hydrocarbon moves up the fractionating column depending upon its boiling point. Let's take an appropriate example for it. Suppose a hydrocarbon, and suppose it boils around 120 degrees centigrade. So moving from 400 all the way to 40, 120 degrees centigrade would be something that lies over here, around over here, maybe a little bit up or more, but I'm trying to give you an idea that where it's going to stop. The closer it is to 400, the bottommost part it is going to stop at, most probably. The closer it is to 40, the higher it is going to go up in the fractionating column. So when the temperature falls to around 120 degrees centigrade, the hydrocarbon will turn into a liquid. It would condense and can be removed at that specific fraction, whichever fraction is that, right? So since smaller molecules have lower boiling points, they usually go high up, which means these are smaller molecules, which also means they have lower boiling point, which means these are bigger molecules. The one that's set at the bottom are bigger molecules. They have higher boiling point. And of course, as soon as I say lower or higher boiling point, you can actually attach all of the properties that are related to it with there. For example, these are going to be less viscous, all right, easier to burn, and at the same time, these are going to be more viscous, and of course, difficult to burn. So that's how we can relate the properties we just studied to their size of molecules or to their boiling points. And from there on onwards, we can understand what kind of uh, uh, hydrocarbons are present in that specific fraction or in that specific part. So we call all of these fractions refinery gas, gasoline, kerosene, diesel oil, fuel oil, bitumen. We have six different fractions that we are talking about here. In different books, you're going to find many different fractions. Some of them are going to fraction them into 9 parts, some of them 8 parts. It can be difficult, it can be easier, but this is actually a simplification. So we kept it simple for your ease. All right. So that's how we have divided them into different fractions, and let's study what those fractions do. So I've already explained this part. Smaller the mass, lower the boiling point, and higher they're going to get up towards the fractionating column, towards its higher or top side. There are some cases in which we cannot condense them into liquids. That those are refinery gases. There are the cases in which we can't even boil them at 400 degrees centigrade temperature. That is bitumen, right? So after finalizing all of this, let's study the uses of these fractions. Now, the first thing first is that most of the fractions in general can be used as fuel. This means they're going to burn in excess of air or oxygen. They're going to form carbon dioxide and water. And they're going to release a lot of heat energy in the process. We can convert that heat energy into different useful forms of other energy types. And that's why we call it a fuel. So we can define the fuel as a substance which, when burned, releases heat energy. And this is one of the easiest definitions of to understanding what fuels are. Now, we were talking about that how we're going to burn them. Methane is one good example. It's the major constituent of natural gas, which is being all around the world to drive cars, to cook food, to keep the homes heated up. And there are many other multiple industrial usages, but mostly as fuel. We can burn octane, which is one of the most important parts of gasoline or petrol. This is C8H18. We can again burn it in excess of oxygen to give carbon dioxide and water and a lot of energy along with that. But we need to understand one part, that this kind of combustion in which we are producing specifically carbon dioxide and water, we call this kind of combustion as complete combustion. In this combustion, the whole process completes since we have excess amount of oxygen. But what if there isn't enough amount of air or oxygen? That combustion type is known as incomplete combustion. Instead of carbon dioxide being formed, which was supposed to form, it forms in complete combustion. But that's not the product in incomplete combustion. In incomplete combustion, you either get carbon soot or carbon monoxide. Carbon soot is usually depicted as just carbon. Carbon monoxide has the formula of CO. Carbon monoxide is not a good product. It's toxic to human beings. This is the reaction that occurs, and carbon monoxide is extremely dangerous. It's colorless, it's odorless, it's very poisonous because it reduces the ability of your blood, and specifically the protein hemoglobin in your blood, to carry the oxygen around the body. Since you don't get enough oxygen, so your vital organs start to die, and this may even result in the death of a person. Moving on, refinery gases are a mixture of methane, ethane, propane, and butane, which are separated into individual gases. We commonly call them liquefied petroleum gases, or LPG, and this is most commonly used around the world for domestic heating and cooking purposes. Then comes gasoline or petrol. It's actually a mixture of hydrocarbons. The top use is car fuel. Then comes kerosene. The top use is aircraft fuel or jet fuel. For domestic and military aircraft actually use kerosene for their working. In the poorer parts of the world, they may be used for heaters or lamps as well, which is definitely not a good idea since the products are not good enough. So it's better to use it for jet fuel only. Well, the next fraction is diesel. It's actually heavy fuel, so it can be used for heavier engines like buses, lorries, some heavier cars, railway engines. Again, a fuel. However, this specific fraction is used to produce organic chemicals, useful ones, in a process we're going to call cracking, and we're going to explain it a little later in the same chapter or the next one. Next up is fuel oil. Fuel oil is also known as ship oil, and as the name suggests, it is actually a fuel for ships, also shown in the diagram. Moving on, the last for the residue was bitumen. Bitumen is a thick black material. It consists of very big molecules. You having very big number of carbon atoms per molecule, and hence it is usually melted and mixed with small pieces of rock. It is usually used to make the top surface of roads. That's why it's a little sticky when used up in heated form. This was as far as we started yesterday. Now we're going to continue with the environmental problems associated with burning of fossil fuels. Since burning of fossil fuels is actually the major source of energy around the world that has been for past few hundred years, but actually this also poses a problem. First of all, when I use the word fossil fuel, it actually consists of coal, gas, and fuels. Coal is the solid form, and as the name suggests, natural gas is the gaseous form. And when I use the word fuels, it actually gives us the liquid form. So the fossil fuels are present in all three states of matter, and all three are taken out of crude oil. When I say the environmental concerns, when we burn them, we produce carbon dioxide, we produce water. Seemingly, carbon dioxide and water are already a part of the environment. We don't think them as problems, but later on we understood that they actually act as greenhouse gases. They have a specific amount in the environment, and whenever that amount increases, they pose a problem to the entire planet. Greenhouse gases, what do? They trap the heat radiated from the Earth's surface, originally coming from the sun. And actually, a lot of people believe that it is leading to the climate change we're currently having. It is trapping more and more heat energy from the sun. It is warming up the entire planet that we call global warming. I hope you might be familiar with the term, since that's actually a hot topic around the world and is a part of internet or social media or different newspapers as well. And this is actually leading to the climate changes that we are currently having, specifically including the severe changes. Now, we are going to discuss different climate changes. Different climate changes are actually composed of different phenomena for air pollution or for water pollution or for soil pollution, land pollution, which we also call it. Different kinds of pollutions and different phenomena are there. So the first phenomenon that we're going to start with is acid rain. As the name suggests, this rain is not just rain, it is actually acidic rain, which means it's not going to be fun, it's going to be actually dangerous. So, what is acid rain mostly composed of? Sulfur dioxide and oxides of nitrogen as a part of the rain. The rain is slightly acidic, the pH is around or more than 5.6 because of dissolved carbon dioxide. So, that was supposed to happen since carbon dioxide was a good part of the atmosphere. But rain with the pH lower than 5.6, that actually poses a problem. We call that rain acid rain. Acid rain is a specific term that is used when the rain is often about 5 pH or less than 5 or mostly about 4. It's because of the presence of various pollutants. When I use the word pollutant, I'm actually talking about anything that can be harmful for the environment, be it harmful for the atmosphere, be it harmful for the living things, be it harmful for animals, plants, or even non-living based structures like statues or buildings or whatever. Now, acid rain is formed when water and oxygen in the atmosphere react with sulfur dioxide and they convert it into sulfuric acid, one of the strongest mineral acids, or various forms of nitrogen oxide to convert them into nitric acid, again a strong acid, SO2 or NOx. Whenever we write NOx, we're actually trying to talk about NO or NO2, since there are different oxides that can convert into nitric acid. So we put the letter X over here. We sometimes also put the letter X over here since sulfur dioxide and sulfur trioxide can be a part. So we may write it as SOx and this one as NOx. That's how we pronounce it. So they mainly come from power stations and factories where we burn fossil fuels, or they may also come from traffic pollution or motor vehicles, right? Fossil fuels contain a small part of sulfur. Now we're going to discuss their sources, how they come into being. Fossil fuels contain a small amount of sulfur. When that sulfur is burnt in oxygen, it produces sulfur dioxide. That's how this gas comes into being and becomes a part of our atmosphere. Now, in the atmosphere, this sulfur dioxide reacts with water, this reacts with oxygen, and is converted into sulfuric acid. This is an important component of acid rain. Actually, the most problematic component of the acid rain as well. When sulfur dioxide reacts with water, a weaker acid, sulfurous acid, comes into being. So whether a weaker acid forms or whether a stronger acid forms, actually they are both acidic, so they're both posing a problem. Whether little or big, that's not the discussion. The discussion is they are both acidic and posing a problem. How does nitrogen oxide or NOx come into being? In petrol engines, sparks are used to ignite the petrol air mixture to power the car. Of course, when temperature in the engine reaches high enough, it allows nitrogen and oxygen in the air to combine. That's how they combine. And when they combine, these nitrogen oxides can be converted into nitric acid. How does that happen? Usually they do not write equations for it, but first they are converted into nitrogen dioxide. I usually ask my students to keep the equations with you. They're going to help you. Uh, Sometimes they come as for balancing of equations, sometimes they discuss further equations. Whether you discuss it that way or not, these are the balanced equations. So nitrogen and oxygen are converted into nitrogen oxide, which further upon oxidation is converted into nitrogen dioxide, which when reacts with oxygen and water further from the environment, is converted into nitric acid. This is the nitric acid we're talking about, which is another major contribution to the acid rain. The acid rain is a major problem. It has a devastating effect on trees, life in lakes, marine environment, or oceans. It kills trees, it kills fish. The water is so acidic it won't support any life at all, which means it kills every marine living being, which includes fish, which includes marine plants as well. It does not even uh, spare any living, non-living things. For example, buildings, limestone buildings, marble statues, both are made of calcium carbonate. They can be attacked by acid rain and they can be defaced or deshaped. This is the reaction. Sulfuric acid can easily dissolve calcium carbonate and convert it into other material, which actually destroys the whole beauty of the buildings or statues to a point where they can collapse. The solution to acid rain involves removing sulfur from fumes. This is done for petrol used in cars. We use the word term scrubbing the gases from power stations. What do? We already know that these gases are going to react with water and is going to produce acids. So in the industry, instead of just letting these gases escape into the environment, we have a long structure, and that structure is consisted of showers. Just like the showers that we use at home for bathing purposes, we have the similar showers in the industry. The gases are supposed to pass through those showers and then they are converted into acids. That those acids are usually treated, right? We neutralize those acids. This is all a part of middle chapters, which we haven't studied probably. So we convert them into normal salts, and then they are not a problem anymore. This process is known as scrubbing. Scrubbing removes any sulfur dioxide or any SOx or any NOx from the factories, or we may use catalytic converter in cars. So we have different ways to handle the acid rain. And since we are trying to handle this acid rain, it is getting effective and we are able to get rid of the problem we were once posed. But we're still in the phase of getting rid of it. So if everyone supports environment, then we can really get rid of our environmental problem, which actually finishes this topic. Moving on, we were discussing about cracking. Let me take you back to the point where we were discussing cracking so I can explain myself. Now, sorry, that wasn't the point. Okay. When we were discussing diesel, I left you with a small point that some of the diesel is converted to more useful organic chemicals, including petrol. Yeah, means we convert diesel into petrol, and the process is known as cracking. This is the process that we are about to study. So we're going to talk about that how a bigger molecular fraction is converted into more useful chemicals by this process. One of those chemicals also includes petrol and gasoline. So how are we going to do it? Let's study it in the cracking portion. So cracking. Most of the fractions from fractional distillation are useful as fuel. Fractions are more useful and more profitable to sell than others. Then what about the other fractions which are less useful and less profitable? There comes the process of cracking playing its role. The amount of each fraction obtained will depend upon the proportions of various hydrocarbons, not the amounts in which they're needed. So the problem is there are far too many long-chain hydrocarbons which are not in such high demand. They're not profitable to sell. There aren't enough shorter chain hydrocarbons which can actually be used as a fuel for cars. So car fuel is one of the most demanded hydrocarbon from the entire set of fractions. So what if we can convert the bigger, less valuable, less useful fractions into smaller, more valuable, more profitable fractions such as car fuel? This would actually solve the entire set of problems. And cracking is the process which is going to do this for us. So far more petrol is needed than can be supplied by just separating crude oil into fractions. So cracking is the process which actually converts long chain alkanes into alkenes and shorter chain, more useful, more profitable alkanes. The big hydrocarbon molecule in fuel oil, for example, which is made up of carbon 14, which means one molecule will have around 14 carbon atoms, not as much needed as much any alkane like octane or the one with 10 carbon atoms, which can be used for petrol. And along with it will come an alkene. Now, for this kind of equation, actually cracking equations are very easier to work with. Notice the total number of carbon atoms over here are 14. So if we get an alkane of 10, of course the alkene will be of 4 carbon atoms. So that's this balance, 10 plus 4 is equal to 14. Pretty easy to balance. At the same time, the hydrogens are also balanced. Take a look, we have 13 hydrogen atoms over here. The alkane consists of 22. So the rest of the 8 would be a part of alkene. So this makes much more sense. Remember, alkane was formalized as CnH2n plus 2. So whatever the number of carbon atoms, hydrogen will double and then 2 added to it. In case of alkene, the general formula was CnH2n, which was pretty simple. The number of hydrogen atoms are exactly double than that of carbon atoms. So a combination of both actually give us an alkane, which is again CnH2n plus 2, but it's just that it's a bigger chain alkane. I hope this all makes sense. So equations like these can always be filled. Remember, you're supposed to form an alkane and an alkene. An alkane cannot be divided into all set of alkanes. That's not a possibility. So never do that. From that I mean alkane giving us alkane plus alkane. You won't be able to balance this kind of equation, so that's not possible. Please do not make this mistake. When an alkane is broken down, it forms an alkane and of course an alkene along with it. That is what you need to do in the papers, since that has been an important past paper question. Now, how catalytic cracking works? Now, we were just calling it cracking. Now, the term catalytic cracking has been used. So keep in mind, we're talking about using catalysts to support this cracking phenomenon. What is a catalyst? A catalyst is any substance that can speed up our reactions for us so that we can get done with our work more quickly. So the fuel oil fraction is heated to give a gas and then passed over a catalyst of silicon dioxide, normally called as silica, or aluminum oxide, normally called as alumina, at about 600 to 700 degrees centigrade. Make sure you remember these facts. Cracking can also be carried out at a higher temperature without a catalyst, that is known as thermal cracking. It's another type of cracking. So one type of cracking is catalytic cracking, and it includes a catalyst. The other type of cracking is thermal cracking, which basically is done at higher temperature. That's what the word therm means. It means heat. So it's done at high heat without the catalyst. So these are the two types of cracking. Well, however, we prefer catalytic cracking since that's better. That's easier. We require less temperature, and using the catalyst makes the whole process quicker for us. So cracking is an example of thermal decomposition. Therm means heat, decomposition means to break down, a breakdown of a molecule with the help of heat. That's what we are doing. We're breaking down a bigger molecule, we are splitting it up into smaller parts on heating. We're just speeding up the whole process by using a chemical we are calling a catalyst. So the majority of hydrocarbons found in crude oil have single bonds between the carbon atoms. But sometimes new carbon-carbon double bonds are formed, which gives you the idea. This is what the alkenes were about. And these single bond mean we're talking about alkanes. I hope you remember that. So take a look. This is the bigger chain alkane we have, and the only thing you see in there are carbon-carbon single bonds, which is actually an identity of an alkane. Alkanes can be identified by the fact that they only have single bonds. Now, when we heat it in the presence of a catalyst, take a look. You have a smaller chain alkane. Again, it can be identified by the single bonds only. And as soon as you see a double bond in here, you get an idea that you're getting alkenes. And yes, it's very much possible that you get more than one kind of alkene. Even though if you count all the black balls, which means carbon atoms in your products and reactants, that's going to be equal. If you calculate all the white balls, which are representing hydrogen in your products and reactants, again, that's going to be equal, right? Molecules have been drawn to show the various covalent bonds. They have been straightened out at the bond angles of 90 degrees for your understanding. Although they are not at 90 degrees, but we intentionally straighten them out so that you can easily understand it. So we intentionally do this, and that's what you have been doing in order to balance carbon atoms. And when we have a longer chain, we keep doing this, drawing the straightened out bond. One at top, one at bottom, one at right, one at left. That's how the way we fulfill the carbon's valency or the carbon's habit of making four single covalent bonds. So this is the way we go with cracking. Cracking equations are easier to understand and to balance. Take a look, we balance the entire thing in a similar way again. So there are 13 carbon atoms in total from the molecule that we're currently cracking. So it's giving us three products, which is 8 plus 3 plus 2, which is equal to 13 carbon atoms. So the total number of hydrogen atoms in the starting molecule, that is the one that's being cracked, are 28 hydrogens. And you'll notice that apart from alkane, the alkenes, when added to the number of hydrogen atoms in alkane, is equal. So 18 plus 6 plus 4 is equal to 48. So that's how easily we balance these equations. A hint and an important one at that: don't worry too much if you can't remember which are gases and which are liquids. State symbols are commonly missed out in organic chemistry. So if in organic chemistry you do not write these state symbols, you don't know whether it's a liquid or a gas or a solid, don't worry about that. You can miss them out and you'll still be rewarded with complete marks. However, I do tend to ask my students to don't forget about the basics, that carbon 1 to carbon 4 usually stuff with one carbon atom or two or three or four, they're usually gases. So at least this is something you can remember. If not the rest, I'm not asking you to remember carbon 10 or carbon 8 or carbon 14 or carbon 20. No, just the easiest ones to remember. That you would know that methane is a gas, that ethane is a gas, that propane is a gas, that butane is a gas. This is what C1 to C4, this is C1 to C4 means. These are gases. At least just remember these, if not the rest of the hydrocarbons. So cracking produces a mixture of alkanes and alkenes. In this case, two different alkenes are produced, propene and ethene. Octane is an alkane that is also formed. Octane, remember, octane C8 or H18 was an important part of petrol or gasoline. So this process is actually converting a bigger, less useful molecule into a far more useful and profitable molecule. Apart from that, the two types of useful molecules are ethene and propene, which make polymers. We're going to find that in chapter number 29, last organic chemistry chapter in the book, and that would discuss what polymers are. However, octane is an important part of gasoline, which is also stated over here. So therefore, there are two very important reasons why oil companies carry out cracking. They produce more petrol that way. Actually, that's a lot of profit to talk about. And they produce alkenes that can be used for making polymers, mostly plastics. Now you'd be amazed to know, sorry, you'll be amazed to know that the plastics are produced from the leftover parts of cracking products. In this cracking product, the molecule was converted into gasoline. Whatever is left over in here, these are actually used to make plastic. So that's a pretty good way. We turned out with a pretty good equation. We converted a less useful molecule into a very profitable petrol or gasoline portion. And whatever was left with was used to make plastics, and plastics are one of the most common stuff around the world. So yeah, that's a very good deal, right? So moving on, the molecule might have split quite differently. All sorts of reactions are happening in a catalytic cracker. Two other possibilities may be, okay, take a look, alkene and alkane, alkene, alkene, and an alkane, or alkenes and hydrogen. So how are we going to put it? Let me boil it down into two simpler parts since they have given you too many possibilities. There's already discussed the possibility before, and they have discussed two more possibilities over here. So boiling it down, it actually is a combination of two important possibilities as a whole, right? That is alkene plus alkane, one possibility. And the other possibility is that alkanes may give you alkenes of different sorts. So that's alkene plus alkene plus hydrogen, right? So this kind of possibility, and these are these possibilities. How do you know it's an alkene? The number of hydrogen atoms are exactly double than that of carbon atoms. That's an alkene right there. That's an alkene. That's an alkene. Alkene, alkene, alkene. That's how you know. The number of hydrogen atoms every single time in all of these examples are exactly the double of carbon atoms. So that's how we identify an alkene. So these two equations have alkanes along with alkenes. The first possibility, this equation has all alkenes. It never produced an alkane, but if you're producing all alkenes, remember there would be a small percentage of hydrogen produced in order to balance the whole thing out. So there will be many other ways in which this particular molecule may have split up. Remember that the fraction being cracked consists of a complex mixture of hydrocarbons and not just one. At the end of cracking, we have equally complex mixture of hydrocarbons that we had start off with the crude oil. So this mixture has to have go through more further fractional distillation to separate out everything into pure compounds. But since the industry is already carrying out some fractional distillation, this it's not difficult for the same industry again to carry out further fractional distillation. So yeah, even after cracking, so crude oil after fractional distillation gave us useful and less useful products, and then we went on with cracking for the less useful products. Then we need to go with the fractional distillation process again to get the pure products, and this time that's the final product that we can actually use or sell out for a good profit. So let's clear it all up. Let's finalize it by the last extension work present at the bottom. In industry, catalytic cracking is done by passing hydrocarbons through a beds of zeolite. Zeolite is actually a mixture of many different catalysts. We call it silicate, at about 500 degrees centigrade and moderate pressures. Apart from breaking down large straight chain molecules into smaller ones, we also have one more process, isomerization, which can occur due to the process produce branched chain alkanes and alkanes with ring structures. The presence of these isomers in the fuel helps increase the number of octane number of fuels. Octane number is actually the measure of a tendency of fuels not go through auto ignition in an engine. We're using too many words that you're not familiar of. So let's define all those words first before you can understand the statement. So fuels may undergo auto-ignition. What is auto-ignition? Auto-ignition is actually when the fuel burns spontaneously out of control. That's not something we would like to do in our car. You'd like to use that fuel for a proper mileage. So you'd like the fuel to burn slowly as you need it and not burn on its own and wear off, or the fuel is consumed wherever when you not even required it. That's actually more like a wastage. That lead to wear and tear in the engine, actually which decreases the life of the engine. So auto ignition is not something anybody would want. So what do? We have a method of calculating whether an auto ignition would happen to a specific fuel in the car or not. In order to calculate it, we measure what? We measure octane number of a system, of a fuel. Actually, octane number is a measure of the quality of fuel. So this discusses the quality of fuel. More the octane number, less would be the auto ignition, and higher would be the quality of fuel, right? So what do? We try to keep the octane number as high as possible, and that ensures a good quality fuel, and least of auto ignition, and maximum engine life. Octane number is something which is represented with a number less than 100. Around the world, that fuel currently being used is anywhere from 92 to 98 octane number, and this number is commonly represented on the top of refueling stations around the world. Next time when you go to refuel your car with petrol or gasoline, go around looking at the banners wherever the names of that specific company is mentioned for the refueling center, the brand names and stuff. And around those, you'll find a number anywhere from this to this. Higher the number means better the fuel, better the quality of fuel that you're getting. If you're getting anywhere something like 92, you might have a lower quality fuel. If it's around 95, or it's around 96, or it's around 98, that means you're getting a very good quality fuel. Next time when you go to a refilling station, you can actually look out for this number somewhere around the refilling station, wherever the banners or the names or the brand images are published, and you can actually look around for the number. And that number is going to help you decide whether the quality of fuel you're having is good or less good. All right. But that's just the extension work. Usually they do not ask questions from these parts. Remember, the extension work are there to make sure that when you go to A levels, you can actually start off with this kind of stuff and this discussion. Usually in all IGCSE, they do not ask you questions from their section work. They stick to the main portion of the chapter. And talking about that, we're done with the chapter. If you have any questions, ask them now.